Have you ever wondered how a simple HTML file can become a professional video? Welcome to the deep dive into Hyperframes, the open-source framework that turns web technologies into frame-accurate video content. In this breakdown, we will investigate exactly how the rendering engine works, how every pixel is computed, and what really happens under the hood from composition to final output. At the heart of Hyperframes lies the composition. A composition is simply an HTML document that defines a video timeline. Every clip, whether it's a video, image, audio track, or animation, lives inside a composition. The root element uses data attributes like data composition ID, data width, and data height to define the canvas. Think of it as a stage where all your elements perform. There are two layers in every composition. First, the HTML layer handles the declarative structure, what plays, when, and on which track. Second, the script layer handles creative animations using GSAP. Clips are discrete blocks on the timeline. A video element becomes a video clip. An image tag becomes an image overlay. Audio tags handle music and voiceovers, and nested div elements become subcompositions. Data attributes control everything. Data start sets when a clip begins. Data duration sets how long it lasts. Data track index controls the Z-ordering, so clips on higher tracks appear in front. You can even use relative timing. Instead of hard coding seconds, you reference other clips by ID. For example, data start equals intro means start when the intro ends. This makes timelines incredibly flexible. GSAP is the animation runtime that powers Hyperframes, but here is the critical difference from typical web animation. GSAP timelines are created paused. The framework controls seeking, not wall clock time. You register your timeline on window.timelines with the key matching your composition ID. The engine then seeks this timeline to the exact frame time before capturing each pixel. During rendering, GSAP internal timeline is overridden, so it runs in lockstep with the output frame. Unlike other tools, where GSAP plays through at real speed, Hyperframes positions every animation frame by frame. Now for the core of how Hyperframes actually renders. The rendering engine uses a seek and capture loop. Step 1, it launches a headless Chrome instance using Chrome Headless Shell. Step 2, the composition HTML is loaded into a browser page. The Hyperframes runtime is injected to manage timeline seeking, clip lifecycle, and media playback. Step 3, for every single frame in the video, the engine calls render seek of time, where time equals floor of frame divided by FPS. This uses integer math. No wall clock involved. Step 4, Chrome's headless experimental begin frame API captures the compositor output as a pixel buffer. This produces pixel-perfect frames without any screen recording artifacts. The captured frame buffers are then handed off to FFmpeg for encoding into the final MP4, WebM, or MOV file. Audio tracks are mixed, volumes applied, and the final video is produced. The frame adapter pattern is Hyperframes' extension point for multiple animation runtimes. Every adapter answers one question: what should the screen look like at frame N? First-party adapters support GSAP, Anime, JS, CSS keyframes, Lottie 3, JS WebGL, and the Web Animations API. Each implements seek frame, init, and destroy methods. The adapter never controls its own clock. It only responds to seek commands from the engine. This is what makes frame-accurate rendering possible across different animation systems. Determinism is the core guarantee. Same composition always produces the same video. Every time. The frame clock uses integer math. There are no wall clock dependencies, no unseated randomness, no render time network fetches, and fixed output parameters. Every frame is independently positioned, making the entire pipeline reproducible and verifiable. The full pipeline orchestrated by the producer package involves several stages. First, loading and compiling the HTML, then injecting the runtime and waiting for readiness gates. Assets like fonts and images must be fully loaded before capture begins. The compiler resolves data start references, probes media durations with ffprobe, and bundles external assets. Multiple workers can capture frames in parallel, each launching a separate Chrome process. This dramatically speeds up rendering. A 30-second video at 30 FPS generates 900 frames, captured one by one. The architecture has 3 core packages. At the base is Hyperframes core, providing types, parsers, the linter, compiler, and runtime. Every other package depends on it. The engine package handles the low-level capture pipeline. It manages Chrome instances, implements the seek and capture loop, and handles frame encoding. It communicates via the window.hf protocol. On top sits the producer, combining engine capture with FFmpeg encoding. It handles the complete HTML to video rendering, including audio mixing, HDR support, and parallel worker management. Why does this matter? Because Hyperframes gives you pixel-perfect, deterministic rendering with frame accuracy. It supports multiple animation runtimes, not just GSAP. You get true code-driven video production. No timeline editors needed. Your version control becomes your video history. And AI agents can create entire video compositions programmatically. To recap, compositions are HTML documents defining video timelines. Clips are elements with data attributes controlling timing. GSAP animations are sought frame by frame, not played in real time. The engine captures each frame via Chrome's Begin Frame API. The producer orchestrates the full pipeline from HTML to MP4, and determinism is guaranteed through integer math and frame adapters. Hyperframes represents a paradigm shift in video production. By leveraging web technologies and browser rendering, it opens up video creation to anyone who can write HTML and CSS. Explore the source code, build your own compositions, and join the open source community. The future of video is code. Thanks for watching.